welcome. Today we will discuss about two special types of functions in mathematics which has got wide applications in calculus. They are the exponential functions and logarithmic functions. Exponential functions and logarithmic functions. Let's start with exponential function. We have seen a function which is always similar to exponential function in our previous analysis, like the power functions. How did the power function look like? Power function was actually of the form some y of x equal to say x raised to a, right? So we have seen such power functions and we know how to conduct the differentiation and other operations on power functions, right? But exponential functions got a difference, and that makes all the behavior different from this power function. And exponential function is a function of the form y of x equal to a raised to x. Remember, in power function we had y of x equal to x raised to a, where we had a variable base and a constant exponent, right? So this is called base, and the power to which it is raised is called the exponent. So in the power function part we had a variable base and a constant exponent. But in exponential function we have a constant base and a variable exponent. The exponent is vary. Alright. So exponential function is generally defined as y of x equal to a raised to x, where a is positive and a is not equal to 1. These two conditions are used to avoid the triviality and the cases where the function does not get defined at all. So an exponential function is generally defined as y of x equal to a raised to x, a greater than 0 and a not equal to 1. See, if a is equal to 1, this will be exactly equal to the constant function 1, since whatever to whatever power we raise, 1 will be left as 1 itself. So we take out the chance of a getting equal to 1. Okay, see, these exponential functions are widely used to demonstrate growths and decays. Growths and decays. See, this can be a growth, growth of a certain kind of bacteria in biology, or this can be the growth of a capital in economics, or whatever, and decay can be same as these things, can be the decay of a capital, or the decay of a radioactive material, or whatever. Exponential functions are generally used to demonstrate growths and decays of or growth and decay phenomena in the nature, or in economics, or other allied parts of science. Right. Now let's see how does the graph of an exponential function look like. Let's choose an example as y equal to 2 raised to x. Okay. So y equal to 2 raised to x will be, see, I'll just give you a rough shape of the graph. It will be of the form see, for x equal to 1, we'll be having 2, right? So I'd go like, suppose this is 2. Okay, so this will grow like this. So as x increases, y grows rapidly, right? Y grows rapidly, and such rapid growths are always explained using these exponential functions. What happens if we have the function y equal to 2 raised to minus x? Is that possible? What happened if we had y equal to 2 raised to minus x? right? So see, what is y raised to 2 raised to minus x? This is nothing but 1 by 2 raised to x, or simply 1 by 2 whole raised to x. Again, this is now of the form y equal to a raised to x, right? So how does it look like? This will be almost like this. Oh, there's a problem here. See, for x equal to 0, if x equal to 0, the y value will be 2 raised to 0, which is equal to 1. And in this case, again, if x equal to 0, y value will be 1 by 2 raised to 0, which is again 1. So for this exponential function, whatever the base, at x equal to 0, the function takes the value 1, right? So this will be of the form. Right. This is how it will look like. Okay, so the red line gives the graph of y equal to 2 raised to x and 2 raised to minus x, and the blue line gives a graph of y is equal to 2 raised to x. Perfect. Now let's see certain properties and examples of exponential function. So consider y equal to a raised to x. What is the domain of this function a raised to x? So domain means the possible values which can be taken by x. See, this statement y is equal to a raised to x is meaningful for every values of x, for every real number values of x. So the domain is the set of all real numbers, or in other words, x can be any random real number. X can take any random real number. And what about the range? Range. What is a range? What do we mean by the range of a function? We have seen that range is the set of all possible values taken by y. Right. So we have assumed that a not equal to 0 and a greater than or equal to 0, or simply a greater than 0 and a not equal to 1. If a is strictly positive, can y be anywhere 0? See, y cannot be 0 until and unless a is 0, and we have assumed that a is strictly greater than 0, so y cannot be 0 anywhere. Is there any possibility that y equal to a raised to x be negative if a is positive? That's also not possible. So the range is actually the set of all positive real numbers. Positive real numbers. Right. The next property. For a is strictly greater than 1. Oh, I hope you remember the graph we have drawn a little ago. For a greater than 1, the function is increasing. The function is increasing. I hope you remember the shape of the graph like this. So the function is increasing, and the concavity nature and is concave upward. Concave upward. Now, see what if a is less than 1? We have seen the case for y equal to 1 by 2 raised to x or 2 raised to minus x. There we had the function like this. Right, almost like this, where the function decreases as x increases, and the concavity does not change, it's still concave upward. Okay, so if a less than 1, function is decreasing and concave upward. The function is increasing and concave upward. And what happened at x equal to 0? At x equal to 0, irrespective of the base, whatever the base, y takes the value 0. So that has to be seriously noted down. X equal to 0 implies y equal to 0. Irrespective of the base, whatever a, we just don't care. At x equal to 0, the function takes the value of 1. So function takes the value of 1. Right. So that's the fundamental information about exponential functions. Remember, the domain is the set of all real numbers. X can be any possible real number. The range is the set of all positive real numbers, since y cannot be negative or 0, since a is not negative and a is not 0. And if a is greater than 1, the function is increasing and concave upward. And if a is strictly less than 1, the function is decreasing and still concave upward. Now let's consider the logarithmic function. Logarithmic function was actually introduced as a possible inverse to the exponential function. Consider the exponential function y equal to a raised to x. It is possible to develop a new function by simply interchanging y and x. The variables y and x, we can obtain x equal to a raised to y. In fact, this is called the logarithmic function, but we may not write it as it is, x equal to a raised to y. Instead, we use another form, y is equal to log to the base a x. So y equal to log to the base a x means nothing but x equal to a raised to y, or in words, y equal to log to the base a x means to get x, the base a has to be raised to the power y. To get x, the base a has to be raised to the power y, which happens exactly here. To get x, the base a is raised to the power y. Right. So this is the logarithmic function. As for exponential function, let's see the graph. Okay. So let's first sketch down the graph of y is equal to 2 raised to x, which we have seen of the form like this, right? And now the graph of the function y equal to log 2 raised to x, log to the base 2x will be like this. See, it has to be arbitrarily closer to its axis. Okay, so it will be almost this form. Alright, so this is how the graph of logarithmic function will look like. And from the mere observation itself, you can observe that these are actually kind of mirror images with respect to a line y equal to x, which gives us the information that both of them acts as inverses to each other. Both of them acts as inverses to each other. And as we have seen for exponential functions, let's observe certain properties. Remember the shape of the graph. What is the domain here? What is the domain of logarithmic function? See, we had the function y equal to log to the base a x, and this mean x equal to a raised to y. Right. So the domain means the set of all possible values which can be taken by x. Right. So what is x? X equal to a raised to y. As we have seen for y equal to a raised to x, we have seen y cannot be negative or y cannot be 0. Similarly, here x cannot be negative or x cannot be 0 since a is non-zero and non-negative. For that reason, x can only be positive. So in this case of logarithmic function, the domain is the set of all positive real numbers. The domain is the set of all positive reals. Right. What is the range? What is the range? See, range is the possible set of all possible values which can be taken by y, and y in this expression x equal to a raised to y does not have any restrictions. Y can be anything, right? Y can be 0, y can be any negative real number, and y can be any positive real number. So the range is the set of all possible y's happens to be the set of all real numbers. All real numbers. All reals or simply in notations R. Okay. So the range happens to be all real numbers. This is exactly bang opposite to the exponential case, where exponential function had domain as all real numbers and range as positive real numbers. But for logarithmic function, the domain is the set of all positive real numbers and the range is all real numbers. Okay. So for base a greater than 1, the function f of x is increasing. Function is increasing and concave down. I hope you remember the shape, right? It was like of this form, not to the left side of y-axis, but arbitrarily close to y-axis. Right? It was of this form. So it's concave downward, and as x increases, even slightly, this thing increases, right? Okay. And for a less than 1, f of x is decreasing. The function is decreasing. And concave upward. You can consider an example for this, right? And for exponential function, we have seen that if x equal to 0, y happens to be 1 irrespective of the base. Similarly, if for the logarithmic function, y equal to log to the base a x, if x is 1, y will be 0 irrespective of the base. If x equal to 1, y will be 0 irrespective of the base, or in other words, simply log to the base a 1 is equal to 0. Okay, so whatever a you have here doesn't matter. The logarithm value of 1 is always 0. So this is about the logarithmic function. Now we can simply compare logarithmic function and exponential function. Before that, you might have observed that inverse nature of logarithmic function. So using that inverse nature, we can just try to rewrite certain statements involving logarithms and exponents. Consider the statement log 16 to the base 2, log to the base 2 16 is equal to 4. What does this mean? This is equivalent to the exponential function, or this is equivalent to saying that, say, log to the base 2 16 equal to 4 means to get 16, 2 has to be raised to the power of 4. 2 has to be raised to the power of 4, or simply 16 equal to 2 raised to 4. Similarly, consider another one. Log to the base 25, 5 is equal to 1 by 2. Which means to get 5, 25 has to be raised to the power 1 by 2. Which means 5 is equal to 25 raised to half, or root of 25, which we know is correct. Right. In the same way, we can transcribe from exponential function to logarithmic function as well, to the back side. That's also possible. Right. So this is how the inverse nature of logarithm and exponential functions are explained. Now let's see a couple of properties of exponential and logarithmic functions. Okay, so for exponential functions, assume a, b are strictly greater than 0, b not equal to 1, let x comma y be any possible real number. We don't restrict x and y. If it is the case, let's examine one by one. A raised to x into a raised to y is equal to a raised to x plus y. You might be familiar with these expressions of exponents, but still for the sake of completeness, we are supposed to go through this. And Second one, a raised to minus x equal to 1 by a raised to x. This 1 by a raised to x makes sense since a is non-zero. A is assumed to be strictly greater than 0, so a raised to x can never be 0, so 1 by a raised to x makes sense. Okay, the third one, a raised to x by a raised to y equal to a raised to x minus y. Okay. Now, let me clear this off. You may note this down. The fourth one, a raised to x whole raised to the power y is equal to a raised to the power xy. A raised to x whole raised to the power y is equal to a raised to xy. And the fifth property is a raised to the power x into b raised to the power x equal to ab raised to the power x. A raised to the power x into b raised to the power x equal to ab raised to the power x. Similarly, a raised to the power x by b raised to the power x equal to a by b all raised to the power x. Okay. So remember these 6 properties of exponential functions. And now let's see the properties for logarithmic functions. To explain the properties of logarithmic functions, let x comma y be any positive real number, and x comma y is a real number. So x comma y be any positive real number, and n be any real number. N can be negative, n can be 0, n can be positive, anything. So n is any random real number, and a not equal to 1 be positive real number. A not equal to 1 be positive real number. So what are our assumptions? X and y are positive real numbers. N can be any real number, and a is a positive real number which is not equal to 1. Okay, so a is not equal to 1 here. If it is the case, we have the properties. 1, log to the base a x y, x into y is equal to log to the base a x plus log to the base a y. Right. The second property, log to the base a x by y equal to log to the base a x minus log to the base a y. Right. Third property is log to the base a x raised to n. Log to the base a x raised to a power of n is equal to n times log to the base a x. N times log to the base a by x, log to the base a x. The fourth property is log to the base a nth root of x. Nth root of x is equal to 1 by n log a x. This can be easily obtained by simply rewriting nth root of x as x raised to 1 by n and using the third property. So these are some properties of exponential function and logarithmic functions, which we will be using in our further analysis of these two functions.